So the first circuit that we're going to be looking at is a circuit in which I have many resistors in series. So series just means that I have one loop, and in them I have placed resistors, at least two. Um, so the overall strategy that we have is to reduce whatever circuit you have with the multiple resistors to a simple circuit, meaning with one voltage source and one resistor. And basically what we say is even if you have multiple batteries, we can think of them as one voltage source with the equivalent voltage of. That's what VEQ means, the net voltage. And all of the resistors can be collapsed into thinking of it as just one resistor. That's REQ, which means it's the equivalent resistance of, that one has the equivalent resistance of however many resistors you have in the circuit, or another word for it is net. So once I find VEQ and REQ, I solve for I, my current, and then I re-expand the circuit and apply R to each individual resistor. It'll make a lot more sense as we go through it. Now note, in a resistors in series, the current remains constant because there's only one loop. So think of it as you're going around in a circle, you're doing something like a conga line or something. The last person can only go as fast as the first person, right? And if you're going around in a circle, then everybody's going to be going at the same rate. And because current is a measure of how many people pass through or how many charges pass through, that will remain constant because it's just one loop. Delta V, how much of the original voltage is used up at each resistor, will depend on how much that resistor is, right? So the current's going to remain the same, but if that current's passing through a really large resistor, something with a really high resistance, it's going to use up more of that original energy than a resistor that has very little resistance. And how much energy I end up using at the end, which is my total delta V, should be equal to the amount of voltage that I had at the beginning, right? So I'm completely using up that energy, and then it's going to be recharged by my voltage source. So it's kind of like thinking of those fountains where the water trickles down, you lose all of the potential energy, and then you use the pump to bring it back up to its original height. So here's my first example. I have two resistors in series, and I know that this is in series because I only have one loop. I have 3 batteries and 2 resistors. My 3 batteries are a 15 volt, another 15 volt, and a 30 volt battery. And I have a resistor that's 8 ohms and one that's 4 ohms. So my VEQ is always going to be the sum of the individual voltage sources. So I just add these up. So 30 plus 15 plus 15 equals 60V. That's my VEQ. And my REQ, basically what's happening is that after the first resistor, I lose some of that original voltage. And then I'm going to lose the remaining voltage at my second resistor. So my total VEQ has to, at the end of here, voltage drop has to equal how much I started here. So because I'm losing voltage here, the push that is left over is decreased. So the total resistance is going to be equal to, the REQ is going to be equal to the sum of the individual resistors. So I'm just going to add these two resistors. 8 plus 4 equals 12 ohms. So rather than thinking about this as a circuit with 3 batteries and 2 resistors, I can think of this as basically being one circuit that has a battery that's 60 volts and it has one resistor that's 12 ohms. Once I do that, I can solve for I. So V is equal to IR. I rearrange to solve for I plug in my values, I solve, and I add my units. So 60 divided by 12 is 5, so my current is 5 amps all the way through. So now we have to look at the voltage drop. So as the I passes through this 8 ohm resistor, right, it has a voltage drop. It loses of the original amount that I had 5 times 8 or 40 volts worth of push, right, power at this 8 ohm resistor. And then as it goes through this 8 ohm resistor, 4 ohm resistor, it will lose 20 volts. V is equal to IR again. My voltage drop is going to be equal to 20. So I lose 40 volts at this resistor, and I lose 20 volts at this resistor for a total of 60 volts, which is what I started out with. The next example, I have 3 resistors, and this is another way of showing your work. So again, I first solve for my VEQ, and my VEQ is going to be equal to 75 plus 15 plus 30. And my REQ, which is going to be 6 ohms plus 9 ohms plus 5 ohms, which equals 20 ohms. So now I look for my current. So 120 divided by 20 is going to be 6 amps. So now I apply that 6 amps at each resistor. So I have my resistor here, 6 ohms, has a current of 6 amps. So my delta V, my change in voltage, is going to be 6 times 6, or 36 volts. At this one, 9 ohm resistor, 6 amp current, my delta V is going to be equal to I times R, 6 times 9, which is 54 volts. And then finally at this 5 ohm resistor, with a 6 amp current, I'm going to drop 30 volts. If I add up all of the voltage drops, 36, 54, and 30, I get 120 volts. So again, this original VEQ right here always has to equal your total of your voltage drops across your resistors in a single loop.